So here, this is how we'll proceed. First, we'll give some introduction, then we'll explain some fuel cell modeling, and then system architecture, and then some simulation result will show how we can implement fuel cell MPPT in MATLAB. Now, in fuel cell, this I already explained in my first lecture, that in fuel cell we have, this is the structure of the fuel cell, where it generates electricity by injecting hydrogen, pure hydrogen from one side and oxygen from other side, where in the electrodes it splits and delivers electron to the load, and then it recombines with oxygen again and exhausts air and hot air and hot water vapor and heat. Okay, so in this process we generate electricity. Definitely we have seen that this voltage is 1.23 volt theoretically, and it goes down to 0.7 volt, because of which we need to connect them in series in order to increase the voltage level for our practical purposes. And here also one thing I explained that day, that this power delivered by this fuel cell depends on how much is the, what is the fuel, what is the rate of fuel flow to the fuel cell. So if we see the curve characteristics, we have seen that day, that here you can see that the voltage characteristics, voltage versus current, which is dependent on fuel flow liter per minute, and also we can see that the power point also shifting. Okay, power is also increasing or reducing if we reduce the fuel flow. So current and voltage, both current voltage both are varying, that's why the power is also varying. So with the fuel flow rate, we need to track how much is the maximum power, and we have to extract maximum power from the fuel cell, which cannot be done by just mere of having a fuel cell. And you, the basic electrical engineering, what it says, that in order to extract maximum power from any source, what you have to do is impedance matching, that you have to do. That impedance matching you cannot do alone, you have to have some power converter. So using that power converter and the fuel cell, we can extract maximum power from the fuel cell. Now from here, Rasmi Ranjan is there to explain. So from here he will explain, and he will end with this simulation. He will execute. He has executed and taken some result, and that he will explain. Over to you.
Thank you very much, sir. Today I am going to explain the fuel cell MPPT application of fuel cell using P&O algorithm. As explained by earlier by sir, this is the, in the previous session we are described, this is the equivalent circuit of fuel cell, which helps us to dynamically, which helps us to predict the fuel cell variation or the fuel cell performance dynamically. So here are the these are the design equation of the fuel cell. Here you can see the cell voltage is defined by nurse voltage and subtracted by sum of the losses that are occurring in the various parameters. Like here in the equivalent circuit, you can see the three resistance are connected. R concentration is the concentration, it represents the concentration loss occurred in the fuel cell, and R arc defines represents the activation loss associated with the fuel cell, and R ohmic is the ohmic loss present in the fuel cell. Here with the help of the using this equation, we can easily model the fuel cell to predict the performances. And these are the two figures associated with the fuel cell. The first figure depicts the polarization curve or voltage versus current curve of the fuel cell. Here you can see three different regions are present with this curve. First one is the activation loss region, and second one is the ohmic loss, and last one is the mass transport loss region. These losses are we have seen in the previous equivalent circuit diagram. And the right side figure represents both the current versus voltage, or the voltage versus current density, and the current density versus power. The left side y-axis represent the voltage with respect to current density, and the right side y-axis represent the power. Here we can see the maximum power occurred at around 45.02 ampere. We can trace the value from the graph, and on the same current value we are getting the voltage value of around 28.94 volt. So with this this is happening at 13 liter per minute of hydrogen flow. And this is your system architecture or the system associated with the fuel cell unit. Here we can see the fuel cell unit is connected to the DC bus by using a boost converter. The converter design is already described in the previous session. With the design equation, we can calculate the fuel, the inductor and capacitor associated capacitor value with the associated system. And this is also explained in the previous session. There are multiple MPPT techniques are existing, such as classical MPPT method or the intelligent or the optimization based MPPT method. There are present, but here we are focusing on the classical MPPT, or that is also called the perturb and observe MPPT algorithm. Here is the basic flow chart of the P&O algorithm. Here we first get the value of voltage and current of fuel cell unit, and after that we will calculate the power. After calculating power, we first compare the power, that is the change in power is greater than 0 or not. If it is greater than 0, then again we compare the change in current. As in the previous session, we see that P&O also work for PV system, but there we are checking for change in voltage with respect to change in power. But with the fuel cell system, we are checking the change in current with respect to change in power. So if the change in current is greater than 0, then duty cycle is adjusted or slightly reduced to meet the exact duty cycle. And if it is the opposite scenario, then the duty cycle will increase. Similarly, if the power change is not less than 0 or not greater than 0 or less than 0, then you also check for another scenario, that is change in current is less than 0 or not. So accordingly, the algorithm will calculate and update the duty cycle to meet the maximum power. Now coming to the simulation. Before we start the simulation, first we have to configure the model or the model parameter. Here you can see the screenshot of that model configuration parameter settings. Here three important things are there. First, simulation time, then simulation it is depending on the solver selection and the solver details. For the simulation time, you can choose it should be started from 0, and we can choose as much any time if you want. For hardware, if it is hardware real time simulation, then it can be up to infinite. But for simulation, due to lack of time, we are choosing only 2 seconds of simulation time. Here another important thing you have to keep in mind, that the solver should be in fixed step. There are two types of solver: fixed step basis and variable step. Here we are choosing fixed step, and the solver should be anyone. But for this simulation, we are taking only ODE 8 and ODE 5. And after setting the solver setting, we have to check the step size. We are taking here as 1 microsecond. Before going to the actual simulation, there are some overview to the components utilized in the fuel cell system. The main component of the fuel cell system is fuel cell stack. This is the path I have given, that will directly go to the fuel cell. By following this path, we can directly add to this model. And after These are also some other components that are used in the modeling. And this is the actual simulation model we have to build in the MATLAB. Now we are going to MATLAB. First we have to create a new blank model, and after this after creating the model, we have to set the model configuration parameter. We can directly go there by pressing Ctrl E or by right clicking and then model configuration parameter. Here we have to give the start time and stop time. For stop time I am giving 2.5 seconds, and solver selection I am giving by default it was a variable step. We have to change it to fixed step. After selecting fixed step, this solver auto it should be showing some various solvers. For this list we are choosing ODE 5, and after that we are going to solver details. The fixed step by default it was auto. For our simulation purpose we are setting it 1 microsecond, and click apply, then OK. Here in this slides I have shown the direct path to fuel cell stack. Let's follow the path and add fuel cell to our model. It can be found in Simscape, electrical, then specialized power system. Go to the library browser, then Simscape, then electrical and specialized power system. Electrical, here you can see the fuel cell stack. Right click and click on the add block to the model, or directly you can press Ctrl I by selecting the block, or you can add by directly searching here. These are different methods to add the component to the model. After adding the model, we have to set the parameters. By using the equation mentioned earlier, we can model we can model the fuel cell by using the equivalent circuit. But for the time constraint, we are using the preset model of the that was provided by MATLAB. Here we are taking the fuel cell PMA proton exchange membrane fuel cell of 1.26 kilowatt of 24 volt. Here also we can use the actual fuel cell by providing the provide the data from the manufacturing data sheet. Here you can, for that purpose we have to choose user defined. Then after that these fields are editable. We can use whatever the parameters available with the manufacturer. For this simulation we are using the preset model. By clicking selecting the preset model, we have to check the parameters of what parameters are available by selecting those model. Here you can see the polarization curve or the plot. By clicking the plot V and VI characteristic, we can see how much power it can generate. See, you can this is the nominal power this fuel cell stack can generate, but it can go up to 2 kilowatt, but this is which is not safe to operate. So for safety purpose, this fuel cell power is limited at 1.26 kilowatt. And for the now you know how much power this fuel cell will operate. Let's see other parameters associated with this fuel cell. By clicking on the fuel cell parameter, another pop-up window will open, and here you can see the stack details. The stack power, nominal power is 1.26 kilowatt or 1259 watt, and maximum power it can go up to 2000 watt. Similarly, the fuel utilization, here you can see at 15.22. This is the by default or the preset model. It can use fuel up to 15.22 standard liter per minute and air up to 36.22 standard liter per minute. To check different or performance of the fuel cell, we can use this signal variation, or we can control the how much fuel we want to give, or how much fuel air flow we want to provide to the fuel cell, so that we can assess the performance of the fuel cell. For that purpose, we can go to signal variation and turn on the what parameter we need to regulate. For this simulation purpose, we are only turning on the fuel flow rate and air flow rate parameters. Now let attach it to the let's attach the converters and load to the simulation. By using this provided path, you can directly go to this component and add it to the model, or directly you can search for the various components, such as for boost converter we need one inductor, to see the different parameters of the fuel cell. We need a bus selector, because the measurement port is the signal, multiple signals are coming across the measurement port, so you have to separate it to see what type of signal you are receiving. Now the converter is complete, and to some measurement device we need to add. Measure the fuel cell voltage and current. Some voltage measurement and current measurement device is implemented. before the converter. By default there are two signals which is not usable for us, so we need to delete it. And these are the signal available with the fuel cell stack voltage, stack current, efficiency, flow rate. These are the parameters available, and but we only need the voltage and current. Let's rename it is as a VFC and current as IFC. And to implement MPPT, we need a function block, MATLAB function block. So where we have to write that code for the algorithm. And to provide the fuel flow and air flow rate, initially we add the two constant block, and that means we are providing constant fuel and constant air flow to the fuel cell unit. Let's give it fuel flow rate at 13 liter per minute and air at 7 liter per minute. And I have previously written the P&O MPPT algorithm code, so I will directly add to the MATLAB function. This is the code by previous algorithm. We have seen first we have to calculate the first get the voltage and current value of the fuel cell, and then calculate it the power. Here in this block we are giving two input, one is IFC and VFC, and then current of the fuel cell and voltage of the fuel cell, and we assign it to two variables, and here in this line we are calculating it to the power, and del V or this is the if and else statement, that is the here this comparison or the assessment was done using this if and else statement in the MATLAB function. The final output of the system will function will be the duty cycle of the duty cycle at MPPT. Here we will provide the voltage and current input to this MATLAB function block. And to keep the duty cycle in range, we are using a saturation block. In the saturation block, we are giving the lower limit at 0 and upper limit at 0.9. So the output of this block should not exceed the 0. It should be limited between 0 and 0.9. And this is the duty cycle. To trigger this IGBT, we need PWM pulse. So we need a PWM converter or PWM generator. And here the switching frequency we are giving 20 kilohertz. Now the MATLAB function block, it has the update method, means at what time it will update the duty cycle. For that we need to edit the data, and the updated method in discrete, and the sample time of the updation we are giving 0.02. This sample time means at every 0.02 second this function block will update the duty cycle of the system. And at last we are adding a power GUI block, and the setting for this are simulation type discrete and sample time 1 microsecond. And to see the result, we are adding the scope and display. To check the power, we are using a multiplier. The MOX will combine the signal and send it to the single display for the viewing purpose. And to receive the parameter, we need a scope with 3 input. And voltage, current and power. The respective ports are connected to its required output. And to see the duty cycle, we also need another scope. Now the duty cycle is tracking. The MPPT algorithm is try to track the power flow.
That is where you kept MPPT.
The power is gradually increasing. Here we are giving the initial duty cycle at 0, so that's why it was taking so much time. If we reduce the initial duty cycle or increase the initial duty cycle, then it might go faster. Now the duty cycle is getting stable. it started tracking now. So you can see the 3-step duty cycle. So the MPPT is working. Presently the fuel cell is giving 1300 watts of at 28 or 29 volt and 45 ampere of current. If you change the fuel flow now, the power will drastically reduce. So to demonstrate that, and now the current fuel flow is at 13 liter per minute. I am reducing, and the fuel cell is giving 1300 watt of power. Now I am reducing it to 9 liter per minute, and let's see what happens. Let's see the duty cycle. The algorithm detect a source variation or the fuel flow variation, and it's recalculated the duty cycle again. The duty cycle is starting to decrease. Now it is getting stable. Again it started to tracking the maximum power point available at maximum power available at 9 liter per minute, which is around 1 kilowatt. So 200 watt of power getting reduced by reducing the fuel flow. This is also works with the source. This is working with the source change. It is also working with the load change. If the load changes and suddenly or gradually, then it is also able to track that change. So to demonstrate that one, I already designed another model in which I have given some timing, so predefined time limit. So where like fuel cell, like fuel flow and load change timing, and also some variable load configuration. Here in this model, we are giving simulation time is same 2.5 second. From 0 to 1 second, we are giving 13 liter per minute, and after 1 second, the fuel flow became 7 liter per minute. And accordingly, similarly for the variable load setup, we are using two load in parallel combination. The first load will last till 0 to 2 second, and the second load is will turn on at 1.5 second and last up to 4 second. But our simulation will stop at 2.5 second. So let's make it 2.5. Here the load is around 2 ohm and 2.8 ohm. So first load will last till 0 to 2 second, and in between another load is turned on and at 1.5 second, and it will last till 0 till end of the simulation. So all other parameters are same. So let's try to run this setup and see the results. What will happen. The power starting to increase. And here the initial duty cycle is also starting from 0. So I will reduce that. Now it is reached the MPP at 13 liter per minute and only one load is operational. So the load is taking around 1270 watt and the source is generating 1300, almost 1300, 1.3 kilowatt, and the rest are getting lost in the system. So you can also see the power, voltage, current and power graph of the MPPT. The power is almost getting average power we are getting here as 1250 to 1260 watts. And the load will source will reduce to at 1 second from 13 liter per minute to 7 liter per minute. The loads fuel flow to the system getting reduced, so the power available at that instant will also reduce from 1300 watt to almost they will get stable at 950 or 900 watt. The duty cycle was also recalculated by the algorithm. Now it is getting stable at around 900 watt or 850 watt. And at 1.5 second, another load will be added to the system. So the overall load of the system will increase. So let's see if that algorithm will try to track it. It is getting 3-step waveform. That means MPPT is working fine. Yeah, another load was added. So there is a drop in voltage and drop in power also. So the algorithm will try to track the maximum power point again. Now it is stable at 0.07, 0.007. And the power is also working at given at maximum power point. Maximum power available at the system is around 850 watt, and the system is consuming 820 watt of power. But at at 2 seconds the load will disconnect, so that will again try to track that changes. That is detected by the algorithm, and the algorithm again try to recalculate the stable duty point. Each point is updated at 0.02 second. So the algorithm perturb at each 0.02 second and observe for the change. If any change is detected, then it try the perturbation again and again try to observe. So that's why the name is perturb and observe. The power is almost MPP at maximum. And we are getting the 3-step waveform for the duty cycle. So MPPT is also working here. So we are tested the source change and load change, both scenario with this MPPT algorithm. So these are the results I have shown. The green color shows the steady state MPPT performance, and at 1 second we seen source change happening, and that the fuel flow changes from fuel flow getting reduced, and this is the voltage waveform of the fuel cell. We are seeing here the voltage is almost constant because it is a voltage source device, and this is the power waveform of the fuel cell. We have seen this graph earlier. Here there is a source change and these two are load change. Here the load is increased, means another load is added to the system. At this change denotes one load shedding, that is one load is removed from the system. And this is the associated duty cycle tracking of the fuel cell. And these are the references. Thank you.
Thank you, Rashmi, for your nice presentation. I was watching this on YouTube. Okay, and then I have seen how nicely you presented. So just one comment I want to add here. Like as I started with saying that only fuel cell will not do. We have to add something which is a converter, power converter. The power converter that is added here is the boost converter, right? So I personally feel the boost converter is one of the best suited for this MPPT tracking for this DC-DC converter, because as I told you, the ripple content to the source should be minimum. Okay, so since a boost converter is having an inductor at the input, so it reduces the ripple current. Contrary to buck converter, where you will see that the source current is discontinuous in nature. So here it is continuous in nature, continuous with some ripple. So this is best suited, and also it's this kind of thing has low voltage, so always you have to boost the voltage. So boost converter works fine with this. Okay, so with this we will close the session, and also we will close for today, because this was the last session. So we'll start tomorrow. Tomorrow I think at 10:30, right? So tomorrow we'll start with 10:30 with C2000 microcontroller demonstration we'll have. Okay. Thank you everyone. Thank you for attending today's sessions. Thank you.